Oh, hello. The year is 1900. Here's Max Planck referring to the period between October to December 1900. After a few weeks of the most strenuous work of my life, the darkness lifted and an unexpected vista began to appear. The problem he was working on, as we know, was that of black body radiation. A black body is one that absorbs all radiation incident upon it. Now, any material which is heated to a sufficiently high temperature, such as the sun or an electric coil, is going to glow. Kirchhoff showed that this is identical to cavity radiation. Now here is a black body. Okay, this is basically a pinhole camera which I constructed, but it's also a cavity. As you can see, I have a pinhole in here. Okay, so you can see that there is a pinhole right up there. Okay, so what happens is when this black body is heated up, the atoms begin to vibrate and they emit radiation, and this radiation bounces around inside the box many times until it equilibrates. That means that the temperature of the radiation is the same as the temperature of the box or the black body. Eventually, of course, the radiation, a ray of radiation escapes through the pinhole. Okay, so that's what we call black body radiation. It was shown experimentally by Stefan in 1879 that the total energy radiated by a black body is proportional to the fourth power of the absolute temperature, and this was proved by Boltzmann in 1884. For the variation with wavelength lambda, Wilhelm Wien obtained the displacement law E lambda equals 1 upon lambda to the power 5 times some function of lambda t, and this was experimentally confirmed by Paschen. In order to provide a theoretical basis for his displacement law, Wien used the Maxwell-Boltzmann distribution for the vibrating atoms of the cavity in order to obtain this expression, which can also be expressed in terms of the energy density U nu. That's the energy density per unit frequency interval around the frequency nu. And that can be related also to the total energy U equals some constant times nu e to the power minus beta nu by t, where beta is also another constant. Enter Max Planck with his thermodynamic approach. Working back from this formula, Planck proposed that the entropy S is given by U by A nu times log of U by EB nu, where A, E, and B are constants. And this leads to del 2S by del U squared is equal to constant by U. And this leads to Wien's radiation law. On the other hand, Lord Rayleigh proposed for the energy density the formula U nu equals 8 pi nu squared kT by C cubed. And this was valid at low frequencies, but it breaks down at high frequencies. As the frequency increases, the energy density goes to infinity, which is obviously impossible. And this was called the ultraviolet catastrophe by Ehrenfest. So the Rayleigh-Jeans radiation law breaks down at high frequencies, leading to the ultraviolet catastrophe. But it is valid for low frequencies, as was experimentally confirmed by Rubens and Kuhlbaum, who presented these findings before the Berlin Academy in October 1900. A few days before the meeting, they communicated these observations to Max Planck. So let's recapitulate. For high frequencies and low temperatures, we have Wien's radiation law, while for low frequencies and high temperatures, we have the Rayleigh-Jeans law. So we have two different laws in two different limits. At high frequency and low temperature, we have Wien's radiation law, which gives del 2s by del u squared is inversely proportional to u, whereas at low frequency and high temperature, we have Rayleigh-Jeans law, which with the previously noted formula implies that the total energy U is proportional to the absolute temperature T. But we know from thermodynamics that del S by del U is equal to 1 upon T, and that led Planck to conclude that the entropy S is proportional to the logarithm of the total energy U, and that gives del 2S by del U squared is inversely proportional to U squared. So, at high frequency and low temperature, we have Wien's radiation law, which gives del 2S by del U squared is inversely proportional to U, whereas at low frequency and high temperature, we have Rayleigh-Jeans law, which gives del 2S by del U squared is inversely proportional to U squared. That led Max Planck to interpolate between these two limits to give del 2S by del U squared is equal to A by U times U plus B, where A and B are constants. Now let's see how this interpolation works. For small u, that is u very much less than b, we can neglect u in the summation in the denominator to give del 2s by del u squared is equal to a by ub, which is equal to constant by u, which is Wien's radiation law. Whereas at for large u, that is u very much greater than b, we can neglect b in the summation in the denominator to give del 2s by del u squared is equal to a by u squared, which gives Rayleigh-Jeans radiation law. As Max Jammer writes in his book The Conceptual Development of Quantum Mechanics, this interpolation, although mathematically a mere trifle, was one of the most significant and momentous contributions ever made in the history of physics. Never in the history of physics was there such an inconspicuous mathematical interpolation with such far-reaching physical and philosophical consequences. Now we know from thermodynamics that del S by del U is equal to 1 upon T, and Planck's interpolation formula gives del 2s by del u squared equals a by u times u plus b. So integrating that expression and equating it to 1 upon t, we get 1 upon t is proportional to logarithm of u plus b by u. Rearranging that expression and taking antilogs on both sides, we get the expression for the total energy, and from there we can get the Planck's radiation law, which is the expression for the energy density in terms of the wavelength or in terms of the frequency. So Planck's formula interpolates between Wien's law and Rayleigh-Jeans law. Wien's law is valid for high frequency and Rayleigh-Jeans law is valid for low frequency, and Planck's law interpolates smoothly between the two and is valid for the entire range of frequencies. As a function of temperature, we know that the energy radiated by a black body is proportional to the fourth power of the absolute temperature. So here we have the distribution of the energy density as a function of wavelength for different values of the temperature. Max Planck presented these equations, which we now call Planck's law of radiation, to the Deutschen Physikalischen Gesellschaft, the German Physical Society, on October 19, 1900, in a paper entitled Über eine Verbesserung der Wienschen Spektralgleichung, that is, on an improvement of Wien's radiation law. Following the session, Rubens worked through the night, checking it against his experimental results, and reported complete agreement, as did Lummer and Pringsheim shortly thereafter. In the 8 weeks following this meeting, the period that we have referred to at the beginning of this video, Planck worked furiously to change the status of his interpolation formula from that of a lucky guess, eine glückliche erratene Interpolationsformel, to that of a statement of real physical significance. To do this, he abandoned his thermodynamic approach and adopted Boltzmann's probabilistic conception of entropy, that is, S equals K log W. Planck now assumed that the total energy consists of an integral number P of energy elements epsilon and interpreted W in Boltzmann's formula as the number of possible ways of distributing P energy elements among n oscillators. Boltzmann's formula is S equals K log W, and Max Planck interpreted W as the number of ways of distributing P energy elements, each of energy epsilon, among n oscillators. This is given by the combinatorial formula W equals n plus p minus 1 factorial divided by n minus 1 factorial times p factorial, and using Stirling's formula, this gives S equals Kn into n plus p log n plus p minus n log n minus p log p, and that can be written in terms of the total energy U and the energy quantum epsilon in terms of this equation, which gives U equals epsilon divided by e to the power epsilon by kt minus 1. And since we know that the total energy is a function of nu by t, comparing it with the previous equation, we must have epsilon equals h nu, and that gives the final Planck's formula. U nu equals 8 pi nu squared by c cubed into h divided by e to the power h by nu kt minus 1. Max Planck presented these results at a meeting of the Deutschen Physikalischen Gesellschaft, German Physical Society, on December 14, 1900, in a paper entitled Über das Gesetz der Energieverteilung im Normalspektrum, on the theory of the energy distribution law of the normal spectrum. Planck describes the motives which led him to postulate the energy quanta. It was an act of desperation because a theoretical explanation had to be supplied at all cost, whatever the price. Of course, as Einstein later pointed out, Planck's derivation was inconsistent, as in his use of Maxwell's electrodynamics, he assumed a continuous wave-like nature of light, but in his use of Boltzmann's statistical formula, he assumed it to be comprised of discrete energy quanta. Planck himself tried repeatedly and unsuccessfully over the years to fit the introduction of H somehow into the framework of classical physics. In any case, until 1905, when Einstein applied Planck's light quantum hypothesis to explain the photoelectric effect, no one took much notice of this new theory. Most physicists regarded the introduction of H as an expedient methodological device of no deeper physical significance. It is ironic that after Einstein's paper on the photoelectric effect, while Planck's formula epsilon equals h nu came to be accepted as indispensable for further progress in the field, Einstein's conception of discrete localized quanta of light was still considered unacceptable. But that is a story for next week. See you then.